So in this video, we'll look at the problem of a spring that's connected to a mass and which is in turn connected to a damper, and we want to find out how this damping affects the motion of the mass and the spring system, right? So what are the characteristics of this damper? So we've known that we can write the equation of motion of the mass by ma, that is the effective force, equal to minus k times x, right? Where k is the spring constant and the mass of the block is m. Okay? Now, if we have damping, we add another term called b times v. Okay. So times. So what this will do is this will try to decrease the motion of the mass. Okay. So here b is a constant and v is the velocity. So the higher the velocity, the lower is the acceleration. Okay. So that's the idea. So now what we can do here is we can write this using differential calculus. So the acceleration here equals d2x by dt square, and v here is nothing but dx over dt. Okay. So we have this equation m times d2x by dt square plus k times x plus b times dx over dt is equal to 0. Okay, so this kind of an equation is called a differential equation, and particularly it is called as an ordinary differential equation or an ODE. Okay, so typically, we will investigate solutions which are similar to harmonics. Okay, which means that the value of x, the displacement here, equal to some constant times e to the power I omega t. Okay, so e to power I omega t essentially equal to cosine of omega t plus I times sine of omega t, where I is the square root of -1. Okay, so essentially what we see here is that both these values, the inside the real and the imaginary part, are solutions to this equation. Okay. So now once we substitute this value, okay, and find the derivatives. So dx over dt equals a times I times omega e power I omega t. Okay, and the d2x divided by dt square equals minus a omega square e power I omega t. Okay, so that's what we get. So what we will do is we will take these expressions, okay, and we'll plug them in here. So let's see what we get. So what we get here is minus m times a times omega square, okay, plus b I a omega, okay, plus k times a times e to power I omega t, and that we set to 0. So we all know that so this value can never be 0. Okay, therefore it is this value that must be 0, right? So and what we do here is we recognize that this is a simple algebraic equation. In fact it's a quadratic. Okay, so let's write it this way: minus m a omega square plus I b a omega plus ka is equal to 0. So this is a quadratic equation in omega. So when we solve for that, we get omega equals minus ib plus minus iba rather plus minus iba square plus 4ma ka. We take the square root of that. We take the square root of that and we divide by negative 2 times ma. Okay, so this is how we find the roots of the quadratic equation. And so what we can do here is this a cancels out with this way and the a square inside and the a square here. So what we have here is equal to minus ib plus minus 4mk minus b square, with the square root of that, divided by, okay, 2m. Okay. So the negative 2, okay, so essentially okay, the negative 2 has been removed here, so therefore we should write this as a plus ib. Okay. So that's essentially what the two roots of omega look like. So we can simplify this further and we can write it this way: I times b divided by 2m plus minus k divided by m minus b square divided by 4m square, and we take the square root of that, right? So essentially, so we found the two roots of omega. So the x here, the displacement, must be written like this, as a times e to the power I times, instead of omega we write this expression I times b divided by 2m plus minus k divided by m minus b square divided by 4m square. We take the square root of that, okay, times t. Okay, so this is a times e to the power I, this is omega, that's t. Okay, so therefore, so here reducing this further, we get x equal to a times e to the power. So now negative I times negative I is I square, and that's negative 1. So a to the power minus b divided by 2m times t, right? Minus b divided by 2m times t, and e to the power plus minus k over m minus b square divided by 4m square times t. Okay, so that's what we get here. So now we can call this as the amplitude, and the amplitude we can write as this is capital B, okay, and we can write this as e to the power plus minus, and there has been an I that's missing, so I will put the I back in, I times k over m minus b square divided by 4m square, okay, so times t, right? So that's what we get here. So now this here we can call as omega prime, okay, so this is nothing but e to the power, so, or sorry, b times e to the power plus minus I omega prime times t. Okay, so we recover the original expression or the form of the original expression. Okay. Now, the interesting thing here is that this can be written as b to the power b times cosine of omega t plus omega prime times t plus I times sine omega prime t times t. Okay. So more generally, okay, if the initial phase is phi, okay, we can write this as b times cosine omega prime t plus phi, okay, plus I times sine omega prime t plus phi, and we can also make these two. We can have two initial phases, phi one and phi two, but this is just a demonstration, so we'll not worry about that right now. Okay, so here the if you just take the real part, and let's say we are interested only in the real part, so we have x equals b times cosine of omega prime t plus phi, okay, with b equals some constant a times e to the power minus bt divided by 2m. Okay, so what we see here is that as t goes to infinity, okay, b actually goes to 0. So which is what we want. The damper should damp out the vibrations in the system, right? But the omega prime, okay, omega prime does not depend on t. Okay, so that's the interesting part. So here what we will get here is if you plot the amplitude as a function of time, the amplitude as a function of time, what we will see is that the amplitude will decay as e to the power minus some constant times t. Okay, so that's what it is, and here the and we multiply that by a, so here the alpha is just b divided by 2n. Okay, and if we plot the displacement as a function of time, right, we see that the initial amplitude is large, but it tends to decay with time, and eventually, so if you take these points here on the very top, okay, so we will see that this is decaying with respect to time, okay, and the same happens here. Okay? Even this decay is with respect to time. Okay, so that's one of the reasons why we mention that the simple harmonic motion in this particular case is damped. Okay, so the damping reduces the amplitude of the vibrations. Now, there is an interesting case to think about, okay, and that is when we have a driven system. Okay, let's say the driver is such that the okay, so the acceleration or the force the force here equals minus k times x, but instead of a negative bv we have a positive bv. Okay, so 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 in this particular case what happens here is that this is a driven system, this is not damped, this is driven, and in this particular case the the vibrations, okay, will not get damped, rather the the vibrations they will increase in amplitude with respect to time. Okay, so So that's essentially um, the outcome of this particular uh, equation. So let's recap. Okay, so let's recap here. So we started out by looking at a spring, a simple spring mass system that's attached to a damper. The damper here is a mass that's attached to a damping reservoir, right? And the behavior of the system is such that, okay, so the damping force acts as negative times a constant times the velocity. So when the velocity is large in magnitude, the acceleration is less. Okay, so what we did was that we converted the, the acceleration and velocity to differential form, and we brought all the terms to the left hand side, so we get this ordinary differential equation, and we are interested in harmonics. Okay, essentially we are interested in functions that are sinusoidal with respect to time. So we can write a general solution for this as x equals a times e to power I times omega t, where e to power I omega t is written as cos omega t plus I sine omega t, and I is the square root of -1. So both the real and the imaginary parts are trig functions or sinusoidally varying functions. So we find the first derivative, the second derivative, and we substitute those in this equation to get this. Okay, this algebraic equation, because e to power I omega t cannot be 0. And then we solve for omega. Okay, when we solve for omega, we get this form. Okay, we get this form here. Okay, and then we can write x as something like this, and we take the term, the leading term, and call that b, and this expression in the square root, we call that omega prime. So we recover the form of the expression that is similar to the expression for simple harmonic vibrations, right? So just to understand the what the damping does to the system, we'll just look at the real part, and and this is an amplitude of b, and b is nothing but some constant a times e to power minus b times t, or 2m, where little b is another constant. So as t goes to infinity, we find that e to the power minus something times t goes to 0. Okay, so this is what is happening. So the amplitude goes to 0, which means that the the sinusoidally varying function diminishes in magnitude. Now, however, if we have a driven system, the effect is the opposite. The amplitude will increase with respect to time. So I hope this gives you an idea for what effect damping has on the simple harmonic motion.